Because it'll cancel out.
Okay, so we are trying some review problems. We've done the one in the middle using integration by parts. Now we're doing the one on the far left with that trig substitution, hoping that that gives us a trig integral that's easier to integrate without all those radical stuff. Walk around and see what trig integral you're getting. Oh, no, that's gonna give us a dang secant.
Really, I'm just gonna watch this.
That should give us a tangent square. Yeah. Yeah, it should give us tangent square.
Did you forget your d theta?
I need to put that right there, so this would be.
Tangent.
What about the x on the bottom?
You change that to secant over 2 and
Get
it
the x on the bottom.
secant over 2 on the bottom.
Yeah, that helps. That gives us a better integral. What's the integral look like? Tan squared? Good. Tan plenty or tan squared?
Oh, no.
Since this is dividing the fractions into 2.
What do you want to do?
Oh, I just did that.
Is there? She's right, 230. All right, so we don't know how to integrate tan squared, right? We don't know how to integrate tan squared. We got a handy dandy trig identity.
Yeah, secant squared minus 1.
Secant squared minus 1 is tan squared. We do know how to integrate secant squared. And if you dig real deep, you might remember how to integrate 1.
What is it, negative? Is it negative natural?
And secant squared has no natural logs. We do have a function whose derivative is secant squared.
Oh.
So we know the antiderivative.
Oh.
It's in there. You had to think. You had to. Is it Monday?
Yes.
Is today Monday?
Yeah.
Happy Monday. I could tell it was Monday because my morning class was all asleep and non-responsive. Couldn't say anything that shocked them. You're my nearly afternoon class, my earliest morning class. You go to the Yes. Was well to West Virginia. Oh, West Virginia. I don't know why. It was nice. Because you're from Houston, and you think everybody goes to Houston every weekend. I'm gonna go ahead and raise the middle one off.
I didn't even watch the game. You go.
Okay, so let's make sure we put everything in correctly. And 2x becomes the secant of theta, so that's secant squared theta minus 1 under the radical sign. X itself becomes 1/2 of secant. And then dx becomes 1/2 secant theta, tan theta, d theta. Want to get rid of some stuff we can. Knock this out. That. Secant squared of theta has a trig identity. That's a tangent squared. We're going to take that out of the radical sign. That's a tangent times a tangent. We'll have to integrate tangent squared. So here's the point where you should realize, I know how to integrate secant squared, but I don't know how to integrate tangent squared, which is okay because tangent squared is secant squared minus 1. And we'll integrate each term. The integral of secant squared is tangent. The integral of 1 is going to be theta. Now we've got to go back and write that stuff in terms of x. So we're going back to here. If the secant of theta is 2x, what are we going to put in for theta? Arcsecant of 2x. And then to get tangent, we'll draw a right triangle with angle theta. Secant is hypotenuse over adjacent, so we can put a 2x here, make the adjacent side 1. And then this leg, when I square it and add it to that, has to give us 2x. So I need to end up with a 2x, and then I need to get rid of the 1.
Where
2x squared.
you get the same thing that was in the radical inverse.
That's right. You can always check. It should be that. And so the tangent is opposite over adjacent. And then our final answer is right here. Opposite. We go ahead and write that as 4x squared minus 1 divided by 1 minus x. And you told me x was going to be the inverse secant of 2x. So that was relatively short with the trig substitution.
Could you also write it as just tan of inverse secant of 2x minus inverse secant of 2x? Like just plug in the arcsecant 2x into the theta.
Oh, the
instead of-
tangent of the inverse secant of 2x, you don't
Yeah.
think that looks clumsy?
Well, it does. I'm just wondering.
Oh, well, I mean, if you like clumsy looking answers. There's nothing wrong with it, it just doesn't, it seems it would need simplifying.
I'm just tempted usually to plug in the.
Just plug in the inverse trig identity.
Yeah.
That's great for now, but what if you have to evaluate the integral? And then you have to plug numbers in. So I said, what if this is a definite integral and theta goes, or x goes from, 0 to 1, and then you've got to do some more work.
Yeah, that's where my mind goes on this.
I can't help where your mind goes, but I can probably try to fix that. Electric shock therapy, other drugs,
Yes, those will both
some
help.
combination. I like to put things in simplified form. Okay, so what was the deal about number 3?
I'm getting to a point, I don't know.
Okay, so let's see, what are we looking for when we've got trig functions with secants and tangents? We need to think of UDUs. So if U is tangent, then the DU has got to be a secant squared. So if we can get a secant squared in here, we're good. If U is secant, then DU is secant tangent. That looks like has no chance. So why don't we see if we can do a UDU with U as tangent, DU is secant squared. We got to get a secant squared in here first. So we're thinking back to this trig identity again, that tangent squared is secant squared minus 1. So let's write that as tangent squared times tangent squared and replace one of the tangent squareds. So let's replace that one with secant squared minus 1. So that minus 1 on the end is a little bit of trouble. Let's just multiply that out and make 2 integrals out of it. I'm going to have a tangent squared times a secant squared. And then I'm going to have a tangent squared times that minus 1. So let's just write that as minus the integral of tangent squared of 2x. Into there? I split it up because this was what I was looking for at the beginning, a U du kind of integral. Let's go ahead and take care of that one, then we'll come back and figure this one out. This won't be hard to figure out because we did it a second ago. So here, for this integral, we take U to be the tangent of 2x. Then du is secant squared of 2x. But now we also get a 2. So I'll keep this here. 1/2 du is the secant squared of 2x dx. So our first integral becomes 1/2 u squared du. Right? This is u squared, that's the du times 1/2. We'll get that integral done in a second. Let's finish this one. So that's 1/2 u cubed over 3. And so from that, we're going to get, let's go in here. U cubed, which is tangent cubed of 2x over 6. Don't know why I got that extra parentheses there, but they're there.
Better to have too much than too little when it comes to parentheses.
I'll have to agree with that. Okay, now what are we gonna do here?
Secant squared minus
Secant
1.
squared minus 1. So secant squared of 2x minus 1 dx. So don't lose the 2. Let's go ahead and take u to be 2x. du then is 2 times dx. And so we get 1/2 du is dx. And so we can write that first integral as a 1/2 integral secant squared of u du. We can write this as a plus 1 dx. Okay with that? Then the integral of secant squared of u is tangent of u, where u is 2x. And then the integral of 1 is just x. So this comes up here. Minus 1/2 tangent of 2x plus x plus c. So it's easy to lose things when you got the 2x in there. You got to worry about the little chain rule actions. So the integral that I had up here originally, the secant to the 4th, works that way as well, except for quicker. Maybe not, right? It's secant squared times secant squared. Yeah, it works almost identically to that. I just erased the answer. Why'd you let me do that?
I
You
thought
guys
we
didn't
were
even
good.
get it written down, did you?
I wrote it down.
Did you?
I'm sorry.
Well, me too. I forgot what it was.
It was,
It's tan cubed of 2x over 6 minus the tangent of 2x over 2 plus x. I'm pretty
There
sure.
we go.
Unless I wrote it down wrong.
I think that's right. Did I lose anybody? I don't know. Make you think of any questions you want to ask me? Homework, integrals that are popping up in your daily lives, anything like that?
They're all, we can-
All weekend, folks come in here just to look at it. I would have written it much more neatly had I known that it wasn't going to be cleaned up.
maybe just add some like artistic flair to it.
Yeah.
Some squiggly lines.
Semantics.
I like it.
I think we can handle that after class if you'd like.
Yeah.
Okay. So are we ready to go to the next section? 7.4?
Partial
We're
fraction.
gonna do partial fraction decomposition.
So for partial fractions, that means that we only get full credit or?
Partial credit on your partial fractions. Ricky. And 7.4 is really gonna be our last new integration technique. Then we're gonna review all of our integration techniques in section 7.5. I think there is a section 7.6. Maybe I'll cover the hyperbolics this semester. I feel like we're going fast.
Let's just do Cal 3 this semester.
I mean.
Then we can, then we next semester, you know, we can all.
It's all goof off for the first week.
Yeah.
Okay, section 7.4, the method of partial fractions.
That's what I did for the first week of this class. I heard that at CP 7.4. This math is ruining my life, I guess. Or maybe it's improving it.
Yeah, I was gonna say, it's enhancing your life.
Is it? But it's like whenever chick takes the pill and gets to use 100% of the brain.
So we're going to use this method to integrate polynomials of the expression. I'm going to call it the top over the bottom as functions of x, where the degree on top where t and d are polynomials. So we don't have funky exponents like half powers or anything like that. They're not hidden in square root signs. Everything's nice polynomial behavior type things. And the degree on top is smaller than the degree on bottom. So in other words, our fraction is in reduced form. And if it's not, what if the degree on top is greater than or equal to the degree on the bottom? Divide first. So we got a fraction in reduced form. My first example is going to look like first case. Case one, that our denominator consists of distinct linear factors. That's the case that we did the last one before we Friday. So suppose we want to integrate 5x minus 12. Let's sneeze. Thank you, scared it away. I want somebody to do the science as to why that works.
It's so annoying.
The premature bless you will scare any sneeze away.
I think it's just that Jack is scary.
I got an x times x minus 4 on the bottom. So if you were to multiply the bottom out, it's a second degree denominator, first degree numerator, so it does satisfy the criteria that our polynomial degree on top is smaller than the degree on the bottom. And we've seen that if we had distinct linear factors, then it came from adding fractions together that has the individual linear factors on the bottom. So we take our integrand out. And say that came from adding a something over x with a something over x minus 4. Right, remember doing that on Friday? And then if the factor is linear, the numerator has to be a degree less, which just makes it a constant. So you've got two unknowns to solve, a constant over x and a different constant over 4. So I like to use uppercase letters of the alphabet. We have to take this algebra problem and solve it for A and B. Once we get them to integrate this, we integrate that thing over x plus that thing over x minus 4. We just got to figure out what A and B are. So last time, the way I did it is I wrote the right-hand side as a single fraction with the common denominator. So I multiplied the first fraction by x minus 4 over x minus 4, the second fraction by x over x, and then I simplified that as a fraction with a's and b's on top, and the x over x minus 4. That's kind of the long way. A quick way to get rid of the denominators everywhere is just to multiply both sides of this equation by x times x minus 4. I'm gonna do it that way this time. So we're operating on the assumption that x is never 0 and x is never 4, which makes sense. Otherwise, the first problem's not even defined. So if I multiply this side by that, I'm left with 5x minus 12. Now over here, I'm going to take a over x and multiply it by that. What's left?
A times x minus 4.
That's right. The x's will cancel, and you'll have a times x minus 4. Now I've got b over x minus 4 times that. Can you see what cancels? X minus 4 cancels, and we got b times x. That's what the numerator would have looked like had I done the common denominator step. And then from there, we collect like terms. I collect my terms that have the x, and I collect the terms that don't have the x. So this side would look like a plus b times x minus 4a. And that polynomial over there has to be this polynomial over here, which means the coefficient of x here has to be the a plus b. The constant term here has to be the constant term there. So from here, we equate coefficients. So we have the coefficient of x. On the left, it's 5. On the right, it's a plus b. Of the constant. On the left, it's negative 12. On the right, it's minus 4a. And from the two equations and two unknowns, we can go ahead and start solving for a and b. The second equation tells us that a has to be 3. Put that in where the a is here. A is 3, then b has to be 2. Okay. Keep them circled so I can find them later, because now I need to use them. A goes on top of the x, b goes on top of the x minus 4. Follow all that? But now this is a real easy problem to integrate, isn't it? What's the integral of 3 over x?
3.
3 times the natural log of x. This is also logarithm. And since the coefficient is 1, if that's u, then du is dx. So this gives you 2 times the natural log of x minus 4. And I think this section is real particular about using the absolute value bars. So if you do this on web work, make sure you put that article of the logarithm in absolute value.
Is this one of the ones where we can only set it up and like,
What do you mean?
are we gonna have to solve for the plus c? But like all the way down to the part where it says plus c?
Most likely not.
Oh,
since
yeah.
Pretty much the entire thing is.
Yeah, I want you to integrate, because not all of them are gonna be logarithms.
Could this also be done as a UDU integral if u is x squared minus 4x?
And then du,
Would be 2x minus 4.
and then how am I gonna get that out of the 5x minus 12?
Is there any way to pull out a constant and get weird fractions? To make it-
Eventually, you're gonna have to do a partial fractions.
Okay.
I can arrange terms so that I could do part of it as a UDU, but eventually you'll have to do partial fractions. Okay, so let me do, I'll let you do another one. I'm gonna put, linear factors down here that are distinct. Let me find one. Back here. Let's try this one. Race. It's the algebra that takes the steps, so I want to see how good your algebra is, how quickly you can find partial fraction decomposition. So let's put, we're going to try to integrate x squared plus x minus 1 divided by x plus 1, 2x minus 1. So if you were to multiply out the denominator, what is the degree of the denominator?
Third degree.
Degree 3, the numerator is degree 2. Always check that first. We've got to have our fraction in reduced form. Degree on top is smaller than the degree on the bottom. And there are no common factors between the top and the bottom. So you're going to break that up into 3 fractions, something over x plus 1, something over 2x minus 1. Let's see if you can find what those numbers are. Something over x. These are all linear factors. Let's have a race. Next. Call out your numbers when you get them, what your A, B, and C are going to be, so we can have something that we can check. Do we have an A, B, or C? I'm going to show you the shortcut next. I'll let you do the long way, and I'll show you the shortcut after you do it the long way. That's just the way I roll.
I got it.
What do you get for A,
A is 1,
B,
negative 1/3,
and C?
negative 1/3.
1, negative 1/3, negative 1/3? Anybody getting those as your A, B, and C? Nobody's responding.
I have no idea if that's right. I think it is, but there's so many things like that in mistake.
Anybody got anything differently? Well, you beat them anyway. We're still doing algebra.
Got A is 1, yes. Which means you have B and C.
Got 3 unknowns, so you need 3 equations. Get your x squared equation, your x to the first equation, and your constant one. And there, you kind of fake it. Let's see, multiply both sides by that denominator. You should get this equation. That's the first step, multiply both sides by that common denominator. The equating coefficients is what takes so long. So I'm not going to do it that way. I'll let you finish since you started it that way. Don't worry, it's just valuable class time you're wasting doing algebra. Did you get? You're not getting there. 3 equations, 3 unknowns, huh?
4 years since we.
I don't know. Did you get different? You got the same thing? 1, negative 1/3, negative 1/3? So how'd you get from 3 equations into 2? We're in agreement. We got the 1 and the 1/3 and the 1/3, give or take a negative somewhere. Try to take your 3 equations and 3 unknowns and just make it 2 equations with 2 unknowns. Pick a variable and sub it out so that you just have the same 2 unknowns. Then sub again, or do some sort of elimination. That's why I said you just kind of start making stuff up as you go. Or you can put it, watch the easy way to do it. So instead of equating coefficients, let's just take I don't know if I can spell this word. Judicious choice of X. For instance, if I take this equation and replace X by -1, 2 of these letters are going to be multiplied by 0, and I'll get B. So if I put a -1 in here on the left, I get -1 squared plus -1 minus 1. If I put -1 here, I get A times 0 plus B times -1 times -3, and then C times 0. So it's going to give me B. On the left-hand side, I'm going to get -1. On the right-hand side, I'm going to get 4 times B, 3 times B. Because 3 times 1 is not 4. 3 times 1 is 3. So B is -1/3. Let's do it again. Pick another choice for X. Can you give me a value of X that's gonna make a factor of 2 drop out? 1/2. So let's let X equal 1/2. And on the left-hand side, I get a 4th plus 1/2 minus 1. 1/2 here and 1/2 here knocks out the A and the B. So I get C times 1/2 times 3/2. So let's see, 1/4 plus 2/4 is 3/4 minus 4/4 is a minus 1/4. Over here I have 3/4 times C. So multiply by 4, get -1 is equal to 3C. So -1/3 is C. One more choice of X.
0.
0. If X is 0, I get -1 over here. X is 0 is going to knock out that factor and that factor. So multiplying by 0 gets rid of B and C. And I have A times 1 times -1. So minus A is -1. Says A is 1. If you make some of the factors drop out, then that's a quick way to do this. Then the next step is to integrate this by integrating these separate fractions with our new values of A, B, and C. So we're left to integrate A, we found that to be 1 over X plus B. B is a -1/3 over X plus 1 plus C is also a -1/3 and a 2X minus 1. They're all logarithms. Be careful on the third one. What do we have to be careful about? It's a U du. Yeah, and this third one, we take U to be 2X minus 1. And du is going to give us a 2dx. So you're going to get another factor of 1/2. You're going to have a 1/2, a -1/3, and then you're integrating 1 over U du. The others don't have that problem because the coefficient of the x's are just 1. So we should get as our final answer 1 times the natural log of x minus 1/3 natural log of x plus 1 minus 1/6 natural log of 2x minus 1 plus c. The calculus part's real easy. It's the algebra in between that takes a while. Especially if I give you time to flounder a bit. But the more denominators you have, however many variables you have to come up with that many equations. Right? 4 equations and 4 unknowns is even longer a problem. So it does help if you can kind of just get rid of some of the factors. Okay, the next case we're going to look at are the case of repeated linear factors. I'll give you a what if fraction, but I'm not gonna solve this one all the way out because it's gonna have too many. Suppose I put an x cubed down here and an x minus 2 squared there. There are several ways I can add fractions together and get an x cubed in the denominator. I can add a something over x with a something over x squared with a something over x cubed. You agree that those have a common denominator of x cubed? So that's that factor with subsequent higher power. So I'm adding that as a linear factor. That makes it repeat, that makes it repeat. So I'm going to say you're going to guess an a over x, a b over x squared, and a c over x cubed. Then the same deal here. To get an x minus 2, I could have added a something over x minus 2 with a something over an x minus 2 squared. Those have the common denominator of x minus 2 squared. So this is what I mean by repeated linear factor. So this would have the following general decomposition. Whatever power you have on the linear factor, you need to repeat fractions 1 power more each time with a constant on top. So if this were an 8th power, I'd have to go all the way up to the 8th power. X minus 2, x minus 2 squared, x minus 2 cubed, blah, blah, blah. Because in general, that list of factors has that as the common denominator. So you can't just assume that some of them will not be there. So I can't just say something over x cubed plus a something over x minus 2 squared. It is possible that I had other factors of lower degree added to them. Okay, but this would be a real long problem. So we're not going to do that. I just wanted to illustrate the distinct linear factor rule. So if you have something that looks like mx plus b to a power of n, then you have to have an mx plus b plus an mx plus b squared plus all the way out to mx plus b to the n. So that's on bottom. Then you have to break it up into repeated linear factors. So let's find an easier example than that one. Let's take 6x minus 11 divided by x minus 1 all squared. Six x minus 11 divided by x minus 1 all squared. The denominator, if you multiplied it out, would be an x squared. The numerator is x to the first, so it is a fraction in reduced form. If I asked you to integrate this one way back in section 7.1, you could probably figure out a way to do this integral with some sort of double substitution. Take u to be x minus 1, and then solve for x, that x is u plus 1, and dx is du. I bet you could write this as a doable integral just with a double substitution. You might want to try it later on. So try later a double substitution, where u is x minus 1, u plus 1 is x, du then is dx. I bet that works out really easily. But that's no fun. Let's try it as a partial fraction decomposition. Let's try breaking up this fraction as a something over x minus 1 plus another something over x minus 1 squared. Then my next step would be to write 6x minus 11 is equal to, and then get rid of those denominators by multiplying both sides by x minus 1 squared. So that leaves me the 6x minus 11 over here. If I put an x minus 1 squared up here, one of the factors will cancel. So I'll have a times x minus 1. If I take the x minus 1 squared here, both factors cancel. So I have b all by itself. Right? Okay, maybe we can quickly do this either way. Equating coefficients is quick, and putting numbers in for x is quick.
Let's just make it x equal 1.
Okay, so if x is 1, I have 6 minus 11 is equal to b. 6 minus 11 is a negative 5. There's b. Now what? Equate coefficients. A is the only one with x, right? See, so here we can do some combination. So 6 is the coefficient of x over here. A is the only thing that has an x over there. And so we're going to integrate 6 over x minus 1 plus negative 5 over x minus 1 squared. Now, the first one I agree is a logarithm integral, but the second one's not. How do you integrate 5 over x minus 1 squared? U to u, right? This one here will be the integral of u to the negative 2 du. This one's a 6 over u. Right? If u is x minus 1, du is dx. So be careful. You're not always going to get logarithm integrals. You get a u to a power when you have repeated factors. So we're going to get 6 times the natural log of u minus 5. This one we integrate by adding 1 to the power and dividing by the new power. So there's minus 5. And then I'm going to get u to the minus 1 over minus 1. So I can make that a plus 5 over u. And u was x minus 1. Let's see what that double substitution looks like, just for the heck of it. Go back and try this. Because I want you to be aware of all your options. Some of them are quicker than others. Right, if u is x minus 1, then u plus 1 is x, and du is dx. So I'm going to have 6 times u plus 1 minus 11 over u squared du. So let's multiply that out. 6u plus 6 minus 11 is 6u minus 5 over u squared. Then what? Separate them. I just have a single term in the bottom. So 6u over u squared minus 5 over u squared. So this becomes the integral of 6 over u minus 5 over u squared. Those look familiar. That's 6 times the natural log of u. And that's plus 5 times u to the minus 1. So 6 times the natural log of x minus 1 plus 5 over x minus 1. So you get the same darn thing. So if you have an impulse to try something else, you think it's going to work quicker, go ahead and try it. But if I put some repeated factors down there, you probably need to do something like this. Okay. So let's look at what happens if you have quadratic factors. So case 3, for prime quadratic factors, so an example of a quadratic factor is x squared minus 1. And x squared minus 1 is not prime because it factors as x minus 1, x plus 1. But x squared plus 1 is prime. X squared minus 1 is not prime. Right? This would be considered the product of distinct linear factors. This is a prime quadratic factor. Okay, so if you have a quadratic factor that's prime, then you have to guess a fraction that has that denominator, and our general rule of the numerator being 1 degree less holds. So if this is second degree factor, we guess a general first degree factor. Why can't I get my alphabet in order?
You're a mathematician, I'm a first grade teacher.
But I know the song. Guess what happens if we have repeated quadratic factors?
We combine both of those concepts.
You have this in the denominator somewhere, then you got to make 3 fractions. A something over x squared plus 1, a something over x squared plus 1 squared, a something over x squared plus 1 cubed. And each one of those has to have a linear factor on top. So there, this one little gizmo here is going to have 6 unknowns. So you're going to have to come up with 6 equations to solve for your 6 unknowns. Doesn't that sound like fun?
It does. Like a party.
All right, so let's do one that has a linear factor and a quadratic factor. Oh gosh, let's not do that one. Good God, no. Let's try this one.
$19.
All right, suppose we want to integrate x plus 1 divided by x times x squared plus 2. Yep, that's it. I got a linear factor in the x, a prime quadratic factor in the x squared plus 2.
Can you solve this as like a matrix? Is there a way to do
Yeah,
that?
you can solve systems of equations in matrix form. I won't give you anything that takes that long, unless I'm hankering for a bonus problem or something.
I was just curious. I don't even remember how to do this. I did them at one point.
Kramer's rule, do it. Okay, you always got to check that the degree on the bottom is higher than the degree on top. This one clearly is. If it's not factored, you've got to factor it. And you got to recognize that this doesn't factor anymore. With a minus sign, it would. With a plus sign, it doesn't. Okay, so our plan is we're going to break that up into a something over x plus a something over x squared plus 2. Let's do that algebra down here separately. Then you always have to remember 1 degree less on top. So up here is just a constant. Here's going to be a first degree factor in the most general form. Okay. Then we can clear fractions by multiplying both sides by that common denominator. And try to solve the equation x plus 1 is equal to, well, you tell me, what happens if I multiply both sides by x times x squared plus 2?
You get a times x squared plus 2. Plus bx plus c times x.
Make sure you put the bx plus c in parentheses. So what's a quick way to find x? A quick way to find a.
Yeah, x equals 0.
Set x equal to 0. If x is 0, both bx and c are multiplied by 0. So if x is 0, we can get a. So there's a 1 over here and 2a over here. And then again, that zeroes that one out. So a is a half. But there aren't any more quickies. I can't make another factor equal to 0 anywhere. There's nothing I can plug in for x here and square it and add to 2 to get a 0. And I already did x is 0. So that's it. That's all I got quick. The rest I'll have to equate coefficients. So let's see. What terms will have an x on it?
C.
Just a plain old x to the first power.
Just see.
Just c, right? Because if you multiply this out, you get bx squared plus cx. So we can get c using the fact that that coefficient of x and this coefficient of x has to be the same. So c is 1. We have a, b is going to be the only other x squared. There's no x squareds on the left side, so that coefficient is 0. On the right side, we'll have an a plus a b. And we already have a. A is a 1/2. So b has to be negative 1/2. Agreed? Did I lose anybody on that? All right, let's put those in that top equation where the a, b, and c were. See if we know how to integrate. A is 1/2. B is negative 1/2, and that goes with the x plus c. C is 1. Can anybody integrate what's left?
Yeah.
Okay, this one's easy, right? This is going to be 1/2 times the natural log of x. Let's see how we're going to integrate this. It would be if that one weren't in the way. Right? That's a UDU, agree?
Split them up.
What about that one? Inverse tangent. So I'll have to break that up into 2 fractions. Negative 1/2 over that. Like that. And then the plus 1 over that. You can split the numerator and make 2 separate problems out of it.
The 1 over 1/2.
I put the 1/2 out front. So this one, we take u to be x squared plus 2. du is going to take care of the x on top. So that's going to give us another 1/2 out there. So that middle integral becomes a negative 1/4 1 over u du. Let's go ahead and finish it then. That's a negative 1/4 times the natural log of u. And in this case, u is x squared plus 2. You said the other one was an arctangent. What do we do with that goofy little 2 out there? Yep. 2 comes from, we always want x squared plus a squared. So think of this as the square root of 2 squared. The integral of 1 over x squared plus a squared is 1 over a arctangent of x over a. So our a is the square root of 2. So this integral gives us 1 over the square root of 2 arctangent of x over the square root of 2.
Are you okay with radicals in the divisor?
Yeah, I'm fine with that. So there's our final answer at the bottom. 1/2 natural log of x minus 1/4 natural log of x squared plus 2 plus 1 over square root of 2 arctangent of x over the square root of 2 plus c. Look like partial fractions, or does it look like there's another way you might want to do that?
I would split that bottom.
Yeah.
I mean, split up the bottom.
It's
Subtract
x
two
to
from the top.
x squared minus 1 squared. And then you
Okay,
can
so the
do that
bottom is
again.
factorable, the top is not. You need to notice something else first.
Just subtract.
Same degree.
Same degree, so we can't just start diving into partial fractions. If the degree on top is not strictly smaller than the degree on the bottom, you gotta divide first. So divide that up, find the whole part plus the remainder of the divisor. You do it by dividing or adding a 0 in a clever way. Figure out how to write that as a whole part plus the remainder of the divisor. So it's not in reduced form. Dividing is easy enough. Adding 0 is easy enough. If you divide, the guy on the outside is the bottom. The guy on the inside is the top. Goes one time. Then you subtract that from the line above it, and I get a remainder of 2. If you did this adding 0 stuff, you can write that as x to the 4th minus 1 plus 1 plus 1. And so the x to the 4th minus 1 over x to the 4th minus 1 gives you the 1. 1 plus 1 gives you the 2 over x to the 4th minus 1. All right, so now let's look at it. Now that looks like, what did I say it was? 1 plus 2 over x to the 4th minus 1. So that first part, you go for partial credit, x. Second one, now you got to do partial fractions. So now we're going to factor x to the 4th minus 1. All right, tell me how it factors.
It becomes x squared.
Like that, right? Difference of squares. This factors yet again. But the last one is prime. Adding 2 terms together that are both positive can't be factored. So that second one involves quite a few steps. We got to break that second integral up into 3 integrals. A over x plus b over x plus 1. But then that last one is quadratic, so we'll have a cx plus d over x squared plus 1. So just for this part, we're going to write that as a over x minus 1 plus b over x plus 1 plus cx plus d over x squared plus 1. You're going to solve for a, b, and c, and then see if we can integrate. These two will be logarithms. This might be a u du. This might be split it up into 2. It might be just an inverse tangent. It's always possible that one of the values is 0. We just don't have time to find it right now. That's all she wrote. Can we do it in a minute? You can do it in a minute?
That's right.
Hey, I'm impressed. This is what we'd solve. Multiply both sides by this denominator. I'll have a x plus 1, x squared plus 1, plus b, x minus 1, x squared plus 1, plus c, x plus d, x minus 1, x plus 1. You have 4 unknowns. You're going to need 4 equations. I think you can let x be 1, x be negative 1. You can even let x be 0. And then you can just pick a random number for x and generate your 4 equations. So remind me, we'll finish that one next time. And we're practicing all together. Oh, wait, you pass back your papers. So if you turned in papers, I got papers. Turn in papers, I got papers. I did some grading. We'll spread them out a little bit so you can see them. You have 2 of them. Really see it myself.
Are you good with that?